as a warm-up for the Graham-Schmidt procedure that we're going to be looking at in the next clip, we're going to talk about projection to a subspace. So suppose first that we've got an orthonormal basis. Then the projection of u to the span of the first vector is, let's call it v1, and it's just going to be given by e1 times the dot product, right? So this is just the standard projection formula. And then just to recap, what we have is that v looks like v1 plus w1, where v1 is in the span of the vector we're interested in, e1, and w1 is perpendicular to v1. Okay, so we saw this from before in the clip where we were talking about the orthogonal decomposition of one vector with respect to another. Okay, so now we can continue. So the projection of v to the span of e1, e2, so now this is a two-dimensional subspace, is going to be v2 rather, given by ve1, e1 plus ve2, e2. And then just as before, we have that v looks like v2 plus w2, where v2 is this thing that we just created in the span of e1, e2, and w2, which is v minus the projection to the span of the first two vectors, is orthogonal. And so we can continue as much as we want. So the projection of v to the span of the first m vectors so that's just the sum of the projections onto each of the first m elements of our orthonormal basis. And just as before, we have that v looks like the part that's in the span of the first m vectors and the rest. So vm is in the span of the first ones, and wm is the leftover part, and it's orthogonal to vm. Okay, and so notice that vm is orthogonal to vm minus 1 as long as v is not orthogonal to the mth vector. So, because if that happens, then you're adding on 0 at the mth step, and so it remains exactly the same. Otherwise, it's going to be orthogonal. And so the way to see this is that if we look at vm minus 1, that's just the thing that we added on in the last step, which is a summand that looks like v against em in the inner product times em. And this is going to be in the span of em, because it's a scalar multiple of em. And we know that em, and therefore its whole span, is orthogonal to the span of everything that came before, because we're assuming this is an orthonormal basis. So, in general, so this is what it looks like if we're looking at like an orthonormal basis and the first few terms of it. But just in general, if U is any subspace of V and we're given some orthonormal basis of U, then we can talk about the projection of V to the subspace U and it's going to be given by looking at the projection onto each of the components of this orthonormal basis and then adding them up. And so that's how you do the projection to a subspace.